So welcome to the Thursday, October 1st Mechanical Engineering Research Seminar. Today we have Dr. Nickolaus Bruno talking about magnetic shape memory alloy solid refrigerants and metrics to measure the performance of those things. So thank you, Nick.
Thanks, Michael. Yes, my name is Nick Bruno, and today the title of my talk is an improved performance metric for comparing magnetocaloric solid-state refrigerants that undergo a first-order magnetostructural phase transition. So as a few points of my talk, I'm going to be just briefly mentioning some background information as why we want to be looking at this kind of metric. I'll talk a little bit about what's called the conventional magnetocaloric effect that occurs in ferromagnetic shape memory or ferromagnetic materials, and a performance metric that was developed in the 1980s called the refrigeration capacity. Talk a little bit about the thermodynamics, materials thermodynamics behind that metric, and then I'll extend ideas to novel shape memory alloys, as metamagnetic shape memory alloys. I'll discuss the thermodynamics for those materials, and then sort of walk you all through a sort of a procedure in developing a new performance metric to compare the performance or magnetocaloric performance of these new materials. So, the problem, right? We all have refrigerators at home and air conditioning units, and their efficiencies, I think, are between like 40 and 60% efficiency. These are used and they consume probably around 40 to 50% of the United States energy production annually. And so there's been some reports that the heating cooling usually takes about 20 quadrillion BTU in the United States. And so it's a big energy consumption. And at home, we have these vapor compression type refrigerator systems that evaporate a liquid refrigerant or condense it to exchange heat, where we have the latent heat of vaporization from some R132 or something. Well, besides the low efficiency, sometimes we have leaks in these systems, and if that refrigerant, specifically CFCs, but CFCs are basically phased out at this point, HCFCs and other chemicals can go up into the stratosphere. They can interact with ultraviolet radiation and decompose, and can actually create a chemical reaction with ozone to decompose ozone. If a chlorine atom is in the stratosphere and decomposes ozone, it will recombine with another oxygen molecule to make O2, and the chemical reaction can occur again and again and cause a devastating effect on the atmosphere. So there's been a lot of talk about replacing conventional vapor compression type refrigeration. Going to the next slide. So one potential solution to replace, I'm not saying it's the absolute solution, but a potential solution would be solid state refrigeration through something called the magnetocaloric effect. This is a diagram of a magnetocaloric refrigeration cycle, where the way it works, we have a solid material in here, in this block, that is exposed to a magnetic field. And it changes the thermodynamic state of the material and actually cools it off. And then when we remove and apply that magnetic field, the material gets hot or it gets cold, and we can flow some thermal transport fluid over the solid material and generate a gradient in the system. So we have a hot temperature reservoir and a cold temperature reservoir. These types of systems have very high coefficients of performance and much higher efficiencies than vapor compression type refrigeration. So the idea behind my talk is to develop a metric, a screening metric, for all these different new types of materials that exhibit this type of behavior. So what is the magnetocaloric effect? I drew a cartoon here to just describe the process. So say we have a solid material that's ferromagnetic and it's slightly below its ferromagnetic Curie point and no magnetic field. We have high magnetic disorder. And usually in materials speak, disorder is entropy. So we have a high amount of entropy in this state under zero magnetic field. What we could do is apply a magnetic field to the material, and it aligns all of our magnetization vectors, and that decreases our disorder. It decreases our entropy. If we apply that magnetic field in insulated conditions, we actually will heat the material up. Well, if we can remove that heat and then decrease the magnetic field really quickly, we can generate this adiabatic demagnetization refrigeration type system. Essentially, it absorbs energy to randomly orient those magnetization vectors again. Then with this cold material placed at some control volume, we can absorb energy to heat it back up, and then we can repeat the process, use it as a heat pump. If we were to look at an entropy versus temperature diagram of this stuff, we have the black curve, which is the entropy temperature response in zero magnetic field. If we apply a magnetic field, we actually get the decrease in entropy, right? So if we apply a magnetic field isothermally, we'll get an isothermal entropy change. If we apply it adiabatically or isentropically, we'll get an adiabatic temperature change. So here is the magnetization versus temperature response of a typical ferromagnetic material. Sort of ignore the lower green curve here. But if we were to use this material as a solid state refrigerant, we would first reach about room temperature is 300 Kelvin. And we'd just cycle magnetic field really quickly and measure what temperature change we get. So how do we use thermodynamics to quantify the magnetocaloric effect? That's the isothermal entropy change and adiabatic temperature. Sorry, isothermal entropy and adiabatic temperature change. Usually this is done with Gibbs free energy, which is derived from internal energy of the system. We have to apply something called a Legendre transform to get into the Gibbs free energy. But we have dG is the change in Gibbs equals volume, dP, which is d pressure, minus entropy, d temperature, minus magnetization, d field. This is bulk magnetization. These are all volumetric properties. So in a isobaric process where we have constant pressure, our dP is 0, constant field, our dH is 0, we can define our entropy by dG dt, or Gibbs free energy, the derivative of Gibbs free energy with respect to temperature. We could do a similar thing for finding our magnetization with Gibbs free energy. It's dG dH, but that's in an isobaric, isothermal process. And then we can, do some math trickery to derive something called the Maxwell relationship. Maxwell relationship is when we take the derivative of S with respect to H and M with respect to T, the other thermodynamic variable, and we see that both of those quantities are equal to the same thing. It's like Schwarz's mathematical theorem or something says that the order of cross differentials don't matter or something. So we have dH ds dH equals dm dt. Maxwell relationship. We can separate the equation and integrate. And what this says is the entropy change, the isothermal entropy change equals the integral of dm dt. That's our thermomagnetic response. And we integrate from 0 to some applied magnetic field. So if you were going to find the entropy change, isothermal entropy change of this material that I show with the graph on the left side here, we would need to find the derivative of this curve, the slope of the curve, and we multiply by some field level. All right, we can also find the thermodynamic expression for the adiabatic temperature change. And to do that, we use the idea of total entropy. ds total equals the sum of all the different parts that can influence your entropy. In a isobaric process, dP is 0. dH is not 0 because we're going to be ramping dH, but our ds total is 0. So we're completely insulated. And from this, we're able to say ds dH is actually equal to dm dt from the previous slide. We can separate it, move it to the other side of the equation, apply second law of thermodynamics that says ds dt is our isobar heat capacity divided by temperature. And we come up with this adiabatic temperature change equals the integral of T on Cp dm dt dh. Okay. And a lot of the times in literature, what you'll see is people will assume that T on Cp is independent of magnetic field, and they pop it out of the integral, and you have an approximate expression here for your adiabatic temperature change, like the thermodynamic conjugate to isothermal entropy change. All right. So these materials are going to be used as solid-state regenerators, solid-state refrigeration, right? And so obviously we're going to be talking about work, thermodynamic work. Now we're all familiar with the Carnot cycle, right? We have the area inside this curve is indicative of the reversible thermal work that we can perform with some refrigerant. We have T versus S. Wood and Potter in the 1980s developed a metric with this Carnot cycle, right? And they called it the refrigeration capacity. So they said, okay, in literature, we have these ferromagnetic materials that we apply magnetic field to. We have a change in entropy, and we have that as a function of temperature. So here I plot delta S, their entropy change is a function of temperature, which is the difference between these two curves. And the cusp here is the ferromagnetic Curie point of our material. So if we want to have a thermodynamic cycle that exhibits reversible thermal work, we can quantify this, the size of this rectangle underneath our delta S curve. And we can use that rectangle if we use the same parameters for all our different materials to compare them. To say, oh, this material might give us more thermal work than this one under some constant magnetic field or some ramped, say like 1 or 2 Tesla applied magnetic field. All right, so the reversible work they found from a Carnot cycle is refrigeration capacity, and that was the isothermal entropy change that was achievable at some cold temperature reservoir, multiplied by what they didn't know, right? What temperature range should we apply this thermal cycle? So they used full width half maximum of the entropy change curve. Kind of ambiguous, like, okay. But if they did it for all the different materials, they could use it as a comparison between what material would give us the best response. All right. So that is 1985, right? Refrigeration capacity. There's a couple things with refrigeration capacity that I want to point out. In ferromagnetic materials, there's no magnetic hysteresis. Okay, so it's totally reversible, right? The idea of the Carnot cycle is total reversible work. We're ramping a magnetic field, we're getting a temperature change. We can do it again and again and again. It's going to be the same thing every single time. The delta T they use for refrigeration capacity is a little ambiguous, full width half maximum. Usually the hot and cold temperature source of the thermodynamic cycle straddles the Curie point. And that's because you get the highest entropy change at the Curie point. All right, but this is the year 2020, right? And now we have new shiny toys, as they say on the slide. What I mean is new materials that do new things, right? Not just ferromagnetic materials. We actually have shape memory alloys that couple different energy domains. This diagram on the right side here shows the different couplings we can get with magnetic shape memory alloys. We have the thermal energy domain, where your thermodynamic variables are entropy and temperature. The mechanical domain, which is stress and strain, and field, or magnetic domain, which is field and magnetization. And these new materials couple these energy domains with a solid state structural transformation. In the video you see repeating here is a nickel titanium shaped memory alloy that's in my lab. It's not magnetic, but it's a demonstration of thermomechanical actuation, nickel titanium. We're actually performing mechanical work by heating this spring up. So if we could play that again. So I have a weight dangling on this nickel titanium spring. I'm sending current through it, about 5.5 amps, which is causing it to joule heating. I'm raising it above some critical transformation temperature, which is transforming the microstructure from a low temperature martensite to a high temperature austenite. And I can do this again and again. It's not going to fatigue the material. There's been some studies on this, but it's not the point of the talk. But it's cool to watch. So these materials exhibit something called thermoelasticity, or the shape memory effect, where at low temperatures we have some, say, twinned martensite. This is a stress versus temperature diagram. If we apply a load, we will actually detwin the martensite, and we get some large deformation. When we unload the detwinned martensite, we can actually recover the shape of the original material by then heating it up across some critical transformation temperatures. If we heat it up, we're going to thermally expand martensites until we get to some austenite start temperature. And when we heat it up beyond austenite start, we actually get a phase transformation from martensite to austenite, where we are no longer non-cubic, we have a different crystal structure. Then if we cool it off, we're going to transform it back to martensite and be in our original shape. These materials also exhibit something called superelasticity. In order for superelasticity to work, you need to be in the high temperature austenite phase, where you have a cubic crystal structure. You can load it with mechanical stress. You get a linear elastic response of austenite, and you'll reach a critical stress where it will trip it. You'll force it into the martensite phase. And I want to just point out, when you force it into the martensite phase, you get a latent heat of transformation because you have a different crystal structure. It's just like latent heat of vaporization in your thermodynamic cycle at home, right, with your refrigerator, your air conditioning unit. So if I compress this material in austenite, it will actually heat up. Then if I release that stress, it gets cold. It's the strangest thing when you're holding it and you actually feel it get cold. And it exhibits some mechanical hysteresis because the friction that's happening inside the material, there's some dissipation. So actually, when I was a graduate student, I polished up a single crystal of nickel iron gallium and looked at it under the microscope to see if I could observe the martensitic transition. So I just used a set screw on the polished material, and I cranked down on the set screw until I could see something. And I did see some martensitic transition take place on the surface. Then when I released that stress by just unscrewing the set screw, it went back to austenite. Not completely, because there's some residual stress in there, but all right. So the thing that makes metamagnetic shape memory alloys unique is that it then throws magnetism into the wrench. Like, it just throws a wrench in everything. So we have magnetic field versus temperature here. Unlike stress, we can apply a magnetic field to the martensite phase, the low temperature phase, to stabilize or to force it into the high temperature phase. So here we have martensite. We apply a magnetic field. We'll magnetize martensite, which is usually non-magnetic. Then we'll push it into the austenite phase, and we get that heat exchange, right? That latent heat of transformation. When we release the field, we go back to martensite. This is a reversible martensitic transformation. We can also heat martensite up, which is, like I said, magnetization versus temperature. Martensite's non-magnetic. We heat it up, maybe we'll have some magnetic transition here, like at the needle temperature or something, some antiferromagnetic material. We'll transform it into the austenite phase, get the latent heat. If we were to continue heating austenite, we're going to reach its ferromagnetic Curie point. So actually, this material is capable of the magnetocaloric effect at two distinct temperatures, one at the Curie point and one at the transformation through latent heat. So taking a closer look at magnetization versus temperature in these materials. We have low temperature martensite that's non-magnetic. If we heat it up, we'll reach some critical temperatures. We'll transform to austenite, heat it up more, demagnetize at the Curie point. We'll come back down, and we have this thermal hysteresis, right? We don't have thermal hysteresis in non-shape memory alloys. One. If we apply a larger field, we're actually going to decrease these transformation temperatures. So the green curve here is, say, like very small field, like 0.05 Tesla or something. The blue curve would be like 7 Tesla, so really large magnetic field. So a fridge magnet, I think, is about 0.2 Tesla or something. You can imagine the really big magnetic field you need. But if we start originally at the martensite finish temperature, we heat our material to that temperature, and then hold temperature constant and ramp magnetic field, eventually our field will be large enough so we'll be in the austenite phase. And you can envision it, or do kind of a thought experiment, you decrease these transformation temperatures at a certain rate as you apply the field. If we looked at the simultaneous magnetization versus applied field curve, we're going to magnetize martensite to this H required, is what I call it. Essentially, that's like shifting this green curve to a point where this initial bend reaches our MF temperature. We're going to push it into the austenite phase until H star. H star means the austenite finish temperature now equals what MF was. Okay, so I want to develop a performance metric to compare all these different metamagnetic shape memory alloys, and I want it to be consistent with the reversibility in non-SMAs. So how do we do that? This is what our delta S versus temperature looks like for a shape memory alloy around its first order transition. This is what a delta S versus T diagram looks like for ferromagnetic material. What do? We just integrate it like they did, like make a box or something, and integrate? I don't think so. We can't do that because it has different reversibility. This material has thermal hysteresis, has losses. This stuff does not. So if we wanted to use the material in a refrigeration cycle, we need to start at this martensite finish temperature. This is an entropy versus temperature diagram. In field is the blue curve, out of field is the green curve. We get a decrease in those transformation temperatures. So we start at the martensite finish temperature, we apply a magnetic field, generates cooling, we absorb energy, we release the magnetic field, and we can do it again and again. But the stipulation is we need that hot temperature reservoir of our thermodynamic cycle to be at the MF temperature. That way, when we come back to it, we can then ramp field again and do it again and again and again. That would be equivalent to our ferromagnetic material that does not exhibit a first order phase transformation. So I say, okay, this is like our maximum thermal work that I can achieve with my metamagnetic shape memory alloy. Instead of a Carnot cycle, I think it's like a Brayton cycle or something. Okay, so this line just compares the ST versus delta ST of both ferromagnetic materials and a metamagnetic shape memory alloy. I noticed, playing with this stuff for a really long time, that these elbows on my delta S versus T curve actually correspond to my critical transformation temperatures in the shape memory alloy. And actually the width of this curve depends on the adiabatic temperature change, what I'm measuring. Notice in the left diagram, we just have this rectangle underneath the delta S versus T curve. And on the right side, I didn't shade the region in the thermal hysteresis, right? Because that's not a reversible temperature region where we can cycle field and get the same thing again and again. So I don't think we can simply do full width half maximum for shape memory alloy. That would actually encompass the entire diagram. And in experimental data, you don't have those critical temperatures labeled. You don't have a feature to find what that is. A lot of the time in the literature, when researchers describe the refrigeration capacity of these materials, they just integrate these curves without any regard to reversibility. So obviously you're going to have huge refrigeration capacity for these things in comparison to non-shape memory alloys because you have a huge entropy change curve. The entropy change is simply the difference in entropy between austenite and martensite phases through the latent heat. All right, so we have a region here that we need to neglect. How do we define the entropy change of a metamagnetic shaped memory alloy across a first order structural phase transformation? With ferromagnetic materials, we just use Gibbs free energy, right? But we have two different phases now. We have a martensite phase, we have an austenite phase. And usually we can't just use like a Gibbs free energy, a single Gibbs free energy. We use equivalents of Gibbs free energy. So the change in austenite Gibbs free energy equals the change in martensite Gibbs free energy. And we can work through it and find what's called the Clausius-Clapeyron relationship. That's delta S, or entropy change from austenite to martensite, equals the magnetization change across the first order transition times what this dH dt. dH dt is the Clausius-Clapeyron slope. The way we find the Clausius-Clapeyron slope is by performing a whole bunch of thermal magnetization measurements under different fields, picking out our critical transformation temperatures and plotting those temperatures with applied field. The slope of those lines gives us our Clausius-Clapeyron slope. Okay. So it's a little different than just a ferromagnetic material. Now here is another diagram of our entropy versus temperature. And I've shaded in our refrigeration capacity. In order for this to work, to get the same reversibility, we need to apply or start at the martensite finish temperature. And if we say, okay, refrigeration capacity equals the delta S at the cold source times delta T, I need to impose some bounds on this in order to keep that same reversibility. Before, the delta S at the cold source is now going to be just the isothermal entropy change, which is the difference between austenite and martensite. We need to assume that the hot temperature reservoir is our martensite finish temperature for the reversibility. And sort of the width of the block is our adiabatic temperature change. If we were to assume that this was our hot temperature reservoir, the AF temperature, and we integrate this whole thing, we're going to have a huge region here that is cyclically irreversible, and it's going to way over approximate what our refrigeration capacity is for shaped memory alloys. And everyone jumps up and down and says they found like this awesome material, but it's not that awesome. So this parameter, delta T adiabatic, is very important, and we need to be able to define that as well. Before we defined it using our DS equation, our entropy, right? But this, again, is not applicable for a solid-to-solid phase transformation. It's only applicable for a single-phase ferromagnetic material across a second-order transition. So there's been some work by an Italian group, Porchari, where they quantified the adiabatic temperature change across a first-order structural phase transformation by using, it's very empirical, they just use the entropy versus temperature diagram and use some similar triangles to come up with this empirical expression. I've actually measured the adiabatic temperature change in these materials and then computed it with both methods across a magnetostructural transition. And the empirical method definitely works a lot better. So I use this metric in my performance metric. Okay, so if we have refrigeration capacity equals delta S, delta T. I substituted the Clausius-Clapeyron expression, my expression for adiabatic temperature change, and crunch it all down, and we get this nice, beautiful expression here for refrigeration capacity that has the same reversibility as a ferromagnetic solid-state coolant. That's for shaped memory alloys, right? Now, okay, still, we're going to get really big refrigeration capacity. With a ferromagnetic material, we can apply 1 Tesla magnetic field and we get some cooling, right? Well, in this material, if we apply 1 Tesla, you can see the whole 1 Tesla line is in that shaded region of the delta S diagram that I said was not useful. Same with 2 Tesla. Well, now, this is a problem, right? we need to account for that thermal hysteresis range, which we kind of did with refrigeration capacity. But I think we need to account for the energy input, right, needed, so coefficient of performance. So in 2015 or something, a German group and others came up with this coefficient of refrigeration performance, which is the reversible thermal work, refrigeration capacity, divided by the work in, right? It's about the same time I had this idea with all of these parameters and everything. They published it before I did. But they did it a little differently than me. This work in is defined as the integral of our magnetization curve about some Curie point. We do have a Curie point, but what we're looking at is our metamagnetic transition, not the Curie point, right? So actually the work input is equivalent to what's called the Zeeman energies, magnetic Zeeman energy. So I propose to do the following to overcome the issues with hysteresis and minimum field levels to use these materials. First, we need to describe our hot temperature reservoir of our cycle at our MF temperature. And our integral for work input needs to be at that MF temperature. We can define work in as the integral from of m dV. B is the applied field. Here we have our magnetization versus applied field. Just looking at this diagram, this is a big assumption that I make, is that we can approximate the energy as a triangle. I wouldn't discount it because we have a little bit of an over approximation here. We're trying to predict the energy, the area under the dashed dot curve. We have under approximation and over approximation. It's pretty close. I haven't done an error analysis on it, but if we assume that the energy in is the size of this triangle, I can define the applied magnetic field needed based off of the sensitivity of these temperatures to shift with magnetic field. So as I apply a field, those temperatures shift, and if I know that sensitivity, I can define how much field it would take to completely transform it based off of transformation temperatures and my Clausius-Clapeyron slope. Crunching this all down into this metric, coefficient of refrigeration performance, it is unitless, I find I can actually quantify this by just 5 basic parameters that are highly reported in the literature. That's the transformation temperatures in zero field, the heat capacity of martensite, so both of those can be obtained with simple calorimetry measurements, the magnetization change across the transition, and the Clausius-Clapeyron slope. So I need thermomagnetic response, and I need calorimetry. So I worked with an undergrad for about 1.5 years or so, working on this performance metric. He helped me do a pretty extensive literature review on nickel manganese-based shape memory alloys. We collected a whole bunch of data, and one thing we found was that the heat capacity of the martensite phase is not widely published. So I was working with Dr. Josti in the metallurgy department to predict what the heat capacity would be in a few compositions with thermocalc, the thermodynamic prediction software. And with those heat capacity measurements, actually I did measure a few heat capacity points on nickel cobalt manganese indium metamagnetic SMA, and it aligned pretty well with my experimental data. So I'm happy with the heat capacity. But with all of this literature review, we made some Ashby style charts. These Ashby charts did not turn out very well. But I was able to plot the CRP as a function of MF temperature, which is my hot temperature reservoir for my thermodynamic cycle. And we did this for nickel, cobalt, manganese, gallium, nickel, cobalt, manganese, tin, indium, aluminum. And surprisingly, I found that nickel, cobalt, manganese, aluminum gives some of the largest CRPs out of all of these materials, and I've never studied this composition before. So I think I should. Now, I drew a little dot here for cobalt, manganese, iron, germanium, which is another material. It has a CRP above 0.8, but this diagram is not showing up properly. And I recently published a paper, Scientific Reports. It's a very interesting shape memory alloy because it exhibits a ferromagnetic martensite phase and a ferromagnetic austenite phase, so they're reversed. I mean, all of the thermodynamics that I talked about are directly applicable to that type of transformation. It's just a little bit different, or you just have to rederive it. So instead of decreasing transformation temperatures by applying field, we increase them, and we'd apply it to the austenite phase instead of the martensite phase. So I've used this parameter for quite a few years to see how my secondary processing or my processing influences the refrigeration performance of some materials. I've used this on planar cast nickel, cobalt, manganese tin ribbons, where I grew grains with secondary heat treatments, and I found that I get bigger or a higher performance, better performance, with the larger grain size to thickness ratios of my material. So the microstructure in materials actually influences their magnetocaloric performance. I've also used this in studying nickel, cobalt, manganese, indium. These materials were all single crystals, and they exhibited different long-range order depending on what thermal treatment I was exposing it to. So I could do a secondary annealing treatment below 900 Kelvin, and I would grow or stabilize in L21 phase. The atoms would be arranged a certain way. And I looked at those at that microstructure with dark field imaging from transmission electron microscopy. And I found that for some reason, the B2 phase, B2 long-range order in these materials gives a much higher CRP. So it's interesting because you can have one composition and you have a wide range of CRP depending on what the microstructure is and the long-range order. So, in conclusion, I defined the magnetocaloric effect of ferromagnetic materials, some thermodynamic properties, and the refrigeration capacity. I extended the idea to first-order phase transformation materials and placed some bounds on my refrigeration capacity and my coefficient of refrigeration performance. Then we did a literature review and collected all this data to compare the different performances of nickel manganese-based metamagnetic SMAs and found that nickel, cobalt, manganese, aluminum, for some reason, gives us a very good CRP. So I need to make some. I have some high purity raw elements, and I just need to arc melt them together and do some study with it. I've used this in the past and found larger grain size to thickness ratio in these materials is better. B2 long range order is better in nickel, cobalt, manganese, indium. And for future work, I need to still compute the CRP for second order phase transformation materials like the ferromagnetic coolants to compare it with this so they have the same reversibility, right? That's the whole point in the beginning. And I also want to better define my interval for my input energy because I just approximated it like a triangle. If I could use a magnetic model to predict that, it would be much better. But then, I mean, I would have more parameters I need to find in the literature, and they would be much less commonly reported, which is kind of counterproductive. But anyway, so thank you for attending, and I will entertain questions.
No, not yet. Go ahead. So is the CRP, is the main goal to be able to compare the materials that you're talking about, or should we be able to compare the common refrigeration materials?
Oh, yeah, so the reversibility is going to be equivalent. So
I guess my follow-up question is how do they compare? What is the normal CRP for?
Yeah, so yeah, and like I said in my future work, I need to I need to compute the CRP for second order phase transformation materials. I do have.
Second order, this.
What's up?
When you say second order, that's like 134A or.
That's the ferromagnetic theory point.
Okay.
Second order, so non-SMEs.
Well, what about just like what we use in our refrigerator right now?
Oh, I have not looked at it.
Okay.
You mean vapor compression refrigeration, CRP?
You know all the cool terms, but yeah, I mean, like just what we use right now, how does it compare to what?
Yeah, so the efficiency of solid state refrigerators can be up to like 80% or something. The vapor compression in your home is like, I think 30 to 50%. Correct me if I'm wrong. I don't know. I think it's as low as 30%.
So we're talking like way better.
Way better.
Right, the volumetric energy density is the problem.
Right. Absolutely.
I think your fridge would have to be huge.
Well, right. I mean, I guess also how exotic are these materials that you're looking at? I mean, how much are they like practical in the workbench, but not practical in the, being
So there
implemented?
are companies that are, they sell magnetic refrigerators. The main issue with them, in my opinion, is they require much larger magnetic fields. And like I showed, you need 3 Tesla at least to get anything reasonable. And in order to use a magnetic field like that, you need a superconducting magnet, right? You need liquid helium to cool the magnet down. You need niobium, some superconductor. And the idea with all of the materials processing that I've done is to try to reduce that field level to permanent magnet levels, which is about 1.8 Tesla or something, with a neodymium iron boron magnet or something. So, yeah, the potential is there, and then also something I didn't talk about at all is the effect of applying stress, because they couple field, stress, and temperature. So there's ways you can actually apply stress to minimize that hysteresis and minimize the magnetic field level needed, but you're still inputting energy, right? The elastocaloric effect. So you still need to put mechanical energy into it in order to get that thermal energy out. And you still have the hysteresis, but instead of magnetic hysteresis, you'll have mechanical hysteresis.
So my question is, so Nick, at the end, you talked about some experimental stuff where we're looking at grain size, the thickness, and how that's affecting COP. So my question is, what do you think's going on in here? What's the underlying mechanism?
So the reason that we get better CRP in larger grains is it has to do with the elastic energy that's stored in the microstructure. So when you're transforming between your austenite to your martensite, you have twin boundaries, the density of those twin boundaries. You can think of it kind of like, how to explain. If you look at the DSC trace, the calorimetry trace, are you familiar with something like that? You get a peak for the latent heat, and you can pick out the elbows of those peaks. That tells you the transformation temperatures. And when you transform from austenite to martensite, you get a broad peak. And when you go from martensite to austenite, you get a narrow peak. But the areas are about the same. And the reason is that you have elastic energy stored in the microstructure. And when you transform back, you recover it like a spring, right? So the elastic energy plays a role. The microstructural elastic energy plays a role in that CRP. With bigger grains, you have less dense martensite boundaries, and so there's less energy stored. Any other questions?
I think there was something in the chat, wasn't there?
Oh, I was asking the peanut gallery if there were any questions.
You said that Germans came up with an empirical expression. You said it was quote unquote a lot better, right?
Yeah.
What does that mean, a lot better? We're talking like same
In
order of magnitude.
comparison with my direct measurements.
Yeah, but does a lot better mean same order of magnitude or?
Yeah, so with the, if I use that first expression for the adiabatic temperature change for non-SMAs to SMAs, I get like, 10 degree, 15 degree temperature change prediction. And what I'm measuring would be like 6. If I use the German method, it's right on.
So again, right on means within the precision of your measurements.
What was a thermocouple? You can have 0.1, no waste or something, right? Accuracy of a K-type thermocouple. All right, thank you guys.
Thank you, Nick.